first element is on the periodic table tells you whether it's ionic or covalent, because everything to the left of the zigzag line is a what? It's ionic, because this is a metal. Because remember, ionic is metals and nonmetals. So if you just look at the first element, if you see it's to the left of the zigzag line, then you know it's ionic because it's a metal. So the first element is a metal. I'm just going to write metal because I don't have room up there. If it's covalent, the first element is a nonmetal. So look at the first one. So the first one, disulfur. Where's sulfur on the periodic table? Is it a metal or a nonmetal? It's a nonmetal. You're looking at S. See, S is to the right of the zigzag line. So since sulfur is a nonmetal, I know that this is covalent. K3PO4. K is what? Potassium. And is it to the right or the left of the zigzag line? Left, so I know it's ionic. Okay, so because sulfur is a nonmetal, I know it's covalent. Because potassium is a metal, then I know it's ionic. All right, what about N3O6? What is N? And it is a nonmetal, so this is a covalent molecule. And then the last one, chromium 2 nitrate, that is a chromium on the periodic table. It's ionic because this is a metal. Okay, so that's how you figure out if something is a metal or a nonmetal. Remember, just look at the first element. Now, in the naming versus the rules, if you have a nonmetal, then remember you've always got to use those number prefixes. So you have mono, di, tri, tetra, penta. You have to use a number prefix with covalent. Whole name of the first element, first part of the second element plus IDE. So that's kind of the same with both of them. But then you're going to insert the number prefixes. So if you see disulfur tetrabromide, how many sulfurs is that? 2. So that's S2. And then how many bromines? 4. So S2. Br4. So the number prefix tells you how many of each you've got. So di tells you 2 sulfur, tetra tells you 4 bromines. How is it different when you name this next one? So the next one, whole name of the metal, first part of the nonmetal plus IDE is the normal. But what's different about K3PO4? It's a polyatomic, right? So you've got to remember that PO4, it's a polyatomic, so you're going to use the name of the polyatomic. So whole name of the first element, so that is potassium. But instead of first part plus IDE, you just use the name of the polyatomic, so that is the phosphate. So this is potassium phosphate. So notice with ionic, there's no number prefixes. Stop. No number prefixes. Whole name of polyatomic. So if you see a CO3, an NO3, an SO4, a PO4, and remember there were 7 of them, so you definitely want to have those as in your list. The name, its charge, and the formula. So what about this next one? So what would I call this next one? Tri. Whole name of the first element, so that is? Yep, so trinitrogen because there's 3 of them. First part of the second element plus that IDE, what's the number for that one? Hex. So it's hex. What's oxygen? Oxygen's called oxide, so it's just hexoxide. So if you said hexoxide, I'd be fine with that. But remember, if you have two vowels, they drop the A of the number prefix. Trinitrogen, you always use the whole name of the first element, first part of the second, plus IDE with the covalent. Now the last one. So the last one, chromium 2 nitrate. This one is probably the most complicated, because if you're going from the formula to the name, you have to write the name, the symbol, assign the charges, swap the charges, and simplify if possible. So chromium 2, what does that mean? It does not mean that there's two chromiums. That's like 50% of the class will say that means there's two of them. What does that Roman numeral 2 tell you? Not the number of chromium, it tells you it tells you what? Because you can have chromium 2 or chromium 3. The Roman numeral tells you the charge. So chromium 2, this means Cr plus 2. Okay, the Roman numeral tells you the charge on the metal. So this one is Cr plus 2. So nitrate, what is the nitrate's formula? It's not nitride, this is nitrate, so it's a polyatomic. So it is NO3, and its charge? It's a -1. Okay, so notice that the charges are not the same. I've got to swap them. So how many chromiums will I end up having? One chromium. How many nitrates?
2.
So that means I have to put what? Remember, if you have a polyatomic and there's more than one, you have to put parentheses, and the number you're going to put down goes outside. So NO3 stays together. I put a parentheses and a 2. That chromium, the plus 2 of the chromium, is going to go outside of the parentheses for the nitrate ion. So you don't break the polyatomic up. You keep it together. Think of it as like one thing. You just put parentheses around it, and then the number goes outside. Okay, now these last 4, these I told you this is the only math in this entire test, okay? Moles, molecules, and grams. So if you see moles, molecules, and grams, you're going to do one of two things. If you see moles and grams, then you know you need to find the formula mass. So remember the gram formula mass, or the formula mass, sometimes they call it the molar mass. It's how many grams would be in 1 mole based on the formula. So this first one, how many moles are in 243 grams of N3O6? So I know what I know. I know 243 grams. And what I want to find is moles, right? So I know 243 grams. I want to find moles. It's a one step, but to go from grams to moles, I need to know how many grams is in 1 mole. And I use the periodic table for that. So I use this formula. So it's N3O6. So if I have N3O6, that's that trinitrin hexoxide. How many nitrogens do I have in that formula?
3.
So I have 3 nitrogens. And how much does each nitrogen weigh? Look at the periodic table, find the atomic mass, round it to a whole number. It is 14. So that if I multiply 14 times 3, that's 52 grams will be the nitrogen. Now I got to do the oxygen. So I have 6 oxygen. How much does each oxygen weigh? 16. So 6 times 16 is 96 grams. Now I just add those together. So it'd be 148. So that is how many grams is in 1 mole. I just add up the mass of each of the atoms in the formula expressed in grams. That tells me That is called the formula mass or the gram formula mass or the molar mass, all mean exactly the same thing. It's just how many grams of that compound is in 1 mole. So if I have 243 grams, I can set this up and do this in one step. I always put down the unit that I've got, what I know goes first, so 243 grams times in a line. What do I put on the bottom? Grams, right? Because remember, whatever you're given is going to go in the bottom in the first step, and the answer I want to get to is moles. So this is what I mean by saying it doesn't take more than one step, but you do have to figure out the formula mass first. What do I put in front of moles? 1. So in these, moles gets the 1, grams gets 148. So now I just take the calculator and I'm going to say 243 and divide it by 148. I'm going to get 1.641891892 moles. Did everybody get that? That's way too exact, right? But that's just all the digits on the calculator all the way across. So I have to go back to my measured number. How many significant figures in my measured number? 3. The 2, the 4, and the 3. So remember, when you go to do the rounding, start with the first significant figure on the left. So the 1, the 6, and the 4. I'm going to keep those. The next number is a 1. So what happens to all the rest of those? They just drop off. So I would end up with 1.64. I would keep the 1.64 and all the rest of that would round so that my numbers of significant figures is the same.
When we take our test, do you want us to put all those numbers first before we round, or just?
You'll just have to get them and make sure that you look at your measured number and use that to do your rounding. Okay? So the other thing to notice I don't use 148 when I try to figure out rounding with significant figures. You don't care. The formula mass is not a measured number. The formula mass came from the periodic table, right? So it's always going to be the number in the problem that I'm going to use. That's why that 243, that's considered a measured number. Okay, so let's do the next one. So the next one, how many moles are in 2.56 times 10 to the 24th molecules? So here, I see moles and I see molecules. When you see moles and molecules, then you know you've got to use Avogadro's number. And Avogadro's number, you don't have to calculate it, you just have to know it. It's 6.02 times 10 to the 23rd molecules is equal to 1 mole. So I don't really have to do any calculating other than just setting this up. So in this, 2.56 times 10 to the 24th molecules. And again, keep the units as you go, times and a line. What unit will I put on the bottom first? I gotta put molecules on the bottom. And then what unit am I gonna put on the top? Moles. Right, because that's what I want as my answer. I know, this door is like not even. Well, no, sometimes I push the door open and it stays propped open all by itself. Not tonight. It's like one of the only doors in this whole building that stays open on its own, but not all the time. Okay, so what do I put in front of moles? A 1. And molecules get 6.02 times 10 to the 23rd. Now here's the part that's the challenge, and it really depends on what kind of calculator you have. Everybody's got a calculator, yes? Okay, so if you have a graphing calculator, like Alana, you've got a graphing calculator, make sure that you put parentheses around your exponents or it will not work. If you have an old school calculator, one of mine, here's how I want you to put this in. Everybody ready? I want you to put 2.56. See the EE button just above number 7? Push EE. Do you see the 2 little zeros? Put a 24. So it should be 2.56 with these a little 24, then divided by 6.02 EE 23, and then equals. If you use the EE button, you don't have to put parentheses. You only have to hit the EE button once, and those two little zeros should show up. When I did this, I got 4.252491694, and that would be moles. Everybody got that? Okay, so if you need to, write your steps down on how you go about, so it's 2.56 EE, I put like EE and like circle it to make it look like a button, and then 24. And then divided by 6.02 EE 23. So again, I can't keep all of this, so what have I got to round this to? Yep, so I got 3 significant figures here. Everybody see that? The 2.56, that's my measured values. So when I come over here, I have 4.25. Those are the first 3 significant figures from the left. Next number's a 2, so what happens to those? They get dropped off, yep. So 4.25 moles would be my answer. If you divide by exponents and you're not using the EE button, you have to use parentheses, because otherwise it will only divide by part of the exponent, not the entire thing. But if you use the EE button, it's kind of nice because it puts everything in parentheses, so you don't have to remember that. All right, how are we going to set up the next one? How many molecules are in 0.45 moles of N3O6? What do I start with? So 0.045 moles times in a line. What goes on the bottom? Moles on the bottom and, yep, what I want on top. So if you see moles and molecules, you know you're just going to use Avogadro's number. 6.02 times 10 to the 23rd goes on top. Moles is going to get the 1. So see if you can solve it. I just want to see if everybody got it. Did you get that? 2.709 times 10 to the 22nd. Okay. How many significant figured in my measured number? Nope.
2.
Just 2. Remember, zeros out front are not significant. They just tell you where the decimal place is. So that 4 and the 5, those are my 2 significant figures. So my answer has to be what? 2.7 times 10 to the 22nd. Don't forget to keep, and molecules, don't forget to keep the exponents. Like, don't drop the exponent off. Make sure you keep that there too. And then the last one. How many grams are in 1.45 moles of magnesium hydroxide? That's MgOH2. So what do I got to find first? I have moles. Moles and, this isn't moles and molecules. This is moles and grams. So I've got to find the formula mass. So this isn't the same molecule. It's not N3O6. This is MgOH2. So I need to find the formula mass for MgOH2. So what do I do first? Okay, I have 1 Mg. How much does each one weigh? Find it on the periodic table. Remember, that's the atomic mass at the bottom. Round it to a whole number, it would be 24. So that's going to be 24 grams. Now OH2, what does that mean? So I have oxygen and hydrogen. How many oxygens? 2, because remember with the parentheses, that means OH with the 2 outside means 2 oxygens and 2 hydrogens. Each oxygen weighs what? So that's going to be 32 grams. 16 and 16 are 32. And then I have 2 hydrogens. Each one of those hydrogens weighs 1. That means I got another 2 grams. So I've got to add all those up. So 24 plus 32 plus 2 is 58. So I have 58 grams in 1 mole. Just remember that I can use it like, think of it like almost like a unit conversion. I can put 58 grams or over 1 mole or 1 mole over 58 grams. I'm saying the same thing. One's just the mass, the other one's just that counting unit of the mole. So I start off with the measured number of 1.45 grams times in a line. What unit do I put on the bottom? Grams. Oh, I'm sorry, I just went backwards, didn't I? Yep, brain cramp, sorry. Okay, so I have 1.45 moles times in a line. Moles goes on the bottom. And what goes on top? Grams. Grams gets the what? Gets the 58. So grams is going to get the formula mass. Moles gets a 1. So I take 1.45 times 58, because they're all across the top, and I get 84.1 grams. Now, what about significant figures? It's the same. So 1.45 moles, 3 significant figures, 84.1, 3 significant figures as well. So I'm set. I don't have to do any rounding. So those are equal significant figures. So one thing that I will really try to press upon you, encourage you to do, is when you do these, put your units down first. Okay? So put your measured number and its unit times in the line, and then make sure you put your unit. I see students all the time like just trying to put the numbers down and kind of skipping the unit. That's when they multiply and when they should divide, or divide when they should multiply. So if you make sure that the unit you're given, put that unit on the bottom, put your answer unit on the top, then fill in the numbers. If you do it that way, then your units will always cancel and you just multiply everything across the top, divide by anything that's in the bottom. Okay? And then always the last thing is make sure you look at your significant figures in the measured number and round your answer that way. Okay? So a little bit of a kind of like review. And if you're finding these ones like you're like, I don't think I have those ionic covalent naming things 100% down. I went through and actually answered all of the ones that we didn't complete in chapter 3, because I think there was like 2 slides that had a lot of problems, like is it ionic or is it covalent? What's the name from the formula or formula from the name? I went through and actually answered them all, and I saved it, and it's posted in Moodle as my chapter 3 marked up PowerPoint. So what you can do is you can actually open up a blank PowerPoint, open up chapter 3, the blank one, and you can just practice them because you know the answers. You can like use the regular PowerPoints that don't have any of my notes on them, and then you can check it to see, am I doing this right? Okay, so that would be a good practice just to go through becoming more familiar and being able to pick up those the polyatomic ions, as well as just reviewing how to use those Roman numerals with chromium, copper, and iron. So where we were last time. So remember last time we were doing some drawing and some writing. So like just as a sort of warm up, I want you to go ahead and give me the name of that last compound down here. Give you a minute. This is that skeletal structure. Find the longest carbon chain and circle it. That's the parent name. Name any hanging groups and list them according to which carbon they hang off of, and then list them alphabetically. Okay, so remember in this, we're gonna find longest carbon chain first, and with the skeletal structure, every corner and an end is a carbon, except for if there's a line going to a chlorine, bromine, fluorine, or iodine. Remember, that's the only time the end of the stick is not a carbon, the end of the stick is a bromine, fluorine, chlorine, or iodine. So in this one, what's the longest carbon chain? Yay. So everybody see carbon 1, 2, 3, 4, 5, 6, 7, there's 8. Okay, now there's also these two down here, but if I count it that way, it'd be 1, 2, 3, 4, 5, 6, 7. So it wouldn't be as long, so I'd want to go with that 8. So that is this, and that makes this the octane. So octane is now its last name. So I have to name the things that are hanging off that are not just hydrogens. So this is a bromo, right? Remember, bromine becomes bromo, chlorine is chloro, iodine is iodo, and fluorine is fluoro. This is a what? It's a 2-carbon group hanging off. 1 carbon's a methyl, 2 carbons is ethyl. Okay, that's step 2. Step 1, find the longest carbon chain and circle it. Step 2, circle and name any non-hydrogen groups. What's step 3? What do I have to know about the bromine and the ethyl? I got to number it. So that's step 3. So remember how I told you to number it. Start from either end. You're going to count in until you get to a non-hydrogen group. So if I come in from the left, bromine is number what? 3. If I come in from the right, ethyl is number 4. That tells me to start on the left. Okay? So just start from the end and come in. Whichever side is closest to the non-hydrogen group, that's going to dictate how you're going to number this. So that means bromine is a, no, not a tri, because that would be 3 bromine. So it's just 3. You put the 3, the number in front of bromo tells you which carbon it's attached to, and the ethyl becomes a 5. Okay, so remember the number tells you which carbon that non-hydrogen group is attached to. It doesn't tell you how many of them there are. It just means 1, really. So which do I got to put first? Yep, so I will actually write this 3 bromo, 5 ethyl, octane. And if you're doing it in mastering and you have to name something they give you the structure of, they don't like any spaces. So that's where those dashes, any place you would put a space, put a dash. If you had multiple numbers, see like the one above, 2, 3, 4, use a comma in between those spaces. To be like 2, 3, 4, dash. They would actually put a dash here. It'd be trimethylheptane. Okay. All right, so we did a bunch of these ones, and then we did some drawing from the name, which I think is easier because the thing is really you can put it all in a nice straight line. You don't have to try and figure out which is the longest carbon chain. You know it. So in this one, so if you're going to do 3-ethyl hexane, you draw this one. 3-ethyl hexane. How do you start this off? You're going to put what? Yep, put 6 carbons in a row, right? Because it's a hexane. So remember, the first thing you're going to do is actually put down the parent chain. So you're just going to put carbon, 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 1, 2, 3, 4, 5, 6. There's the hexane. Now remember, carbon always has 4 covalent bonds. The ones we're talking about, they're all single bonds. So there's always going to be a bond up, down, left, and right. So next thing to do, first, you put down the parent chain, put down the number of carbons. Second thing that you do is I want to put an ethyl on carbon number 3. So you can start from the right or left and count in 3. That's fine, right? So if I was going to number 1, 2, 3, 4, 5, 6, right? So this means that I have to put in ethyl. So an ethyl is a 2-carbon group. Each of those carbons has 4 single covalent bonds, bond up, down, left, and right. And remember that if I was going to do a true Lewis structure, I would have all these hydrogens drawn out. These are all H's. Anywhere there's an empty dash, there's an H. That's an ethyl group. Now I told you, you can do it any way you want. If you like doing the Lewis structures, just make sure your carbons always have a bond up, down, and left and right when they're in a chain. You could also do it as a condensed structural formula. What would I call carbon 1? It would be, if it's a carbon with 3 hydrogens around it, condensed structural formula, CH3. Carbon number 2 would be CH2. Carbon 3 would be a CH, and then sticking off would be a CH2, CH3 group. That's the ethyl group coming off. 4 is CH2, 5 is CH2, and 6 would be CH3. So does everybody see how that condensed structural formula, that would be an option as well, just so you know, like this and that are the difference. They're the same molecule. First one's a Lewis structure, second one is considered a condensed structural formula. So you basically just put the carbons and the hydrogens straight in a line that belong to the parent chain and then hang off or stick above non-hydrogen groups, okay? And it's totally up to you. Like you could have done that CH2, CH3 sticking up. It just would have needed to have 2 carbons to it and be on carbon number 3. Then the last one, so how many lines would I do if I wanted to do a skeletal structure? My longest carbon chain is 6, so how many lines in my zigzag? 5. Because remember we said that there would always be one less line in the zigzag than number of carbons in that chain. So it would go 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5. And if you count 1, 2, 3, 4, 5, 6, you have 6 ends and corners in this one. And then I've got to put a CH2, CH3. So what's that going to look like? A methyl looks just like a stick coming off, right? But an ethyl looks almost like an L, kind of like it comes down but has a bend because there's 2 carbons to it. So this would be carbon 1, carbon 2. This is going to be carbon 3. So it would come down and have a bend. So that little bend would be a carbon and the very end would be a carbon. So that would be my ethyl group. So I told you when you have this on a test, you can do any of the 3. You're not going to have to do one or the other specifically. So whichever one you find easier to do, doesn't matter to me. What about 1-bromo, 3-iodo, cyclopentane? What are you going to do for the parent? How are you going to put the parent? 5 what? But they are, what else is this different about this name? What do you need? So that means I need to put it in a ring, right? So remember, think of cyclo, like a cycle. So think of cyclo means a ring of 5 carbons. So that means I've got to do, because it's this. So that's the parent chain in this one. So remember that carbon still has 4 bonds. So each of these carbons will have 2 dashes connected. Do everybody see that that's 4? So in that one, every carbon will have 2 extra dashes. Whatever we don't put non-hydrogen groups on, those would be hydrogens. So 1-bromo, 3-iodo. Where do I need to put the bromo? Anywhere, right? You can put it anywhere. You're just going to call wherever you put it, that's going to be carbon 1. Because in a ring, we could like flip it around, flip it around. So as long as it's in 1, you just choose. So she said, let's put the bromine here. We're going to call that carbon 1 then. So that means I got to put carbon 3. I'm going to put the iodine. So that means I've got to number my chain. You can go clockwise or counterclockwise. It doesn't matter. But the thing is my iodine has to be like 2 carbons away from my bromine. So if this is carbon 1, 2, 3, 4, and 5, then this is where my iodine is. If I numbered counterclockwise, then I'd put my iodine on the other one. But do you see that I could like pick this molecule up and flip it and it would look exactly the same? Okay. So that's where it doesn't matter how you number it. The big thing is make sure that wherever you number it, your bromine's on 1, your iodine's on 3. Is that it? No other non-hydrogen groups, right? So that means all those empty dashes are hydrogens. So if I was drawing a true Lewis structure, I would add all of that. Now, if I was going to do it as a condensed structural formula, I would still have the carbons in that ring, but I would just write how many hydrogens were attached to each of those carbons. So carbon 1 would be what? CH. And then sticking up would be a Br. And then coming down, this would be, carbon 2 would be a CH2, right? Because that carbon has 2 hydrogens. Then the next one coming down would be a CH. And then sticking off would be its iodine. Then I'd come across, and this would be carbon 4 is a CH2. And then coming up to carbon 5, it would be, and then going back across. I mean, that's not the best pentagon, but you get the idea. Got out of control. Doesn't really matter. As long as it's 5 carbons all in a ring, if the bonds are a little bit different in length, I'm not gonna complain. Okay, but again, do you see that the only things that I've got, I like group together the carbons and the hydrogens with the condensed structural formula, and have the non-hydrogen groups are like sticking off. Now if I did skeletal structure, what would it look like? I would just put the house. So that's just like a house with the roof caving in, but. Okay, so I'd have this 5-sided little pentagon, and then you would have a BR. And it wouldn't really matter where it was sticking, it would just be sticking off, and then an I. So bromine on 1, iodine 2 carbons away. So that would be 1 bromo, 3 iodo cyclopentane. So now, I don't know if you've tried this, but in chapter 3, actually, and in chapter 4, there's some of what they call the ChemDraw questions. So it sort of looks like a little pad that you have to click and try to like build a molecule with bonds. So sometimes that drives students crazy. I will tell you the best way to do this, if you have to use the ChemDraw and like build 1 bromo, 3 iodo cyclopentane, the first thing you want to put down on the little pad are the atoms. Okay, you want to put the atoms down where they belong. This is in mastering chemistry. So put the atoms first. So what I would do is I would click on carbon and I'd put my carbons where they go. So like for this one, I would put 5 carbons and make them look like the outline of the house. So I'd put 5 carbons spaced out. If you do that, there's a good chance it's going to put a CH4, 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 CH4. It's just because ChemDraw is trying to give carbon automatically its 4 bonds. So if it doesn't, don't like be like, why are those hydrogens there? That's okay, they'll go away as you build the molecule. So what I would do is I would put the carbons all down, then I would click on bromine and I'd put a bromine up. And I'll tell you it'll put like Br2. And you're like, why are there 2 bromines? That'll go away. Just put your bromine down, switch to iodine, put your iodine down. Once you get all the atoms down that are not hydrogen, then go to the bonds. So like the carbon is either along the bottom or down the side, but the bonds, it just looks like a little diagonal line tab. When you click on it, it'll let you click 1 bond, 2 bonds, 3 bonds. You can choose single, double, and triple bonds. Just click a single bond. Once that's highlighted, take your cursor and hover over the carbon. When you do, that carbon will like turn bright green. Like it'll become like highlighted in green. Click with your mouse and drag to the atom you want to connect. So what I would do is like go for this one. I would hover over this top carbon. It turns green. I click on it and drag to this carbon and let go, and it'll make a bond. And then do the same thing. Connect the second and the third carbon, the third and the fourth and the fifth till I get the ring. Then hover over the bromine. When it turns green, click on it and attach it to the right carbon. And as you do that, you'll see the number of hydrogens will change. The hydrogens will fix themselves. You're really just laying down the atoms, then connecting them. That is really the easiest way. Because if you start trying to put a carbon and connect it to another carbon, what you end up doing is putting down like 5 carbons. And then you're like, wait, that's too many carbons. So then you end up having to like start all over again. And you're like, there's carbons everywhere. It's like, it can get really kind of hairy, but the best thing to do is just put the carbons down where you want them to be, add the bromine and the iodine, then switch over to bonds and then connect them. And if you do it that way, you won't be fighting with it so much, I promise. Okay, so that's just one that I saw that students always have the challenge of. So we've talked about naming molecules based on their structure, drawing them based on their name. There is kind of this midsection in this chapter where they talk about what they call functional groups. So functional groups are really atoms that have molecules that have certain atoms and they have a specific name. In fact, we've actually talked about a couple of them. One of the ones that we talked about, I can't stand these pictures. One of the ones that we talked about were alkanes. Okay, alkanes, we said, are all single carbon to carbon bonds. So all the bonds between carbon are single. Carbon always has 4 covalent bonds. So that's why like pentane, hexane, that ANE ending, those are alkanes. They say when you have all single to carbon bonds, you can't add anything to the molecule because it's already all single. They call those saturated. So that's another term. Saturated is all single bonds. But there are organic molecules that have 1 or more double bonds. If they have a double bond, then they use the term alkene. So alkanes are all single. Alkenes have 1 or more double bonds. They give you some names like beta carotene, if you've ever heard of that, that's like a B vitamin. Beta carotene, that ends in ENE, that is because it's got a double bond there. Limonene has that double bond. Pinene, another one that has that double bond in there. But that ENE is the common ending for something that has a double bond. I will say that double bonds, they're strong, but they're more reactive. Double bonds will typically break before a single bond will. That'll come into play in chapter 5, the next chapter. There's also a triple bond. They're not very common, but they do exist, where you have a carbon with a triple bond to another carbon. Now you remember in lab, when you built the triple bonds, you had to really bend those long sticks to get them to come together, and it was really kind of tight. I think we did it with nitrogen and carbon in lab. They call these alkynes with a Y. So ANE are all single bonds, ENE are the double bonds between carbons, and YNE would be a triple bond. Alkynes are not very stable, they're very reactive, and you don't see them very common in nature. But I do like the little tree frog. In South America, there are frogs that have extremely bright colors. There are frogs that are bright red, like fire engine red. There are frogs that are like bright blue. There are frogs that are bright orange. These frogs, though, they secrete a toxin in the mucus on the surface of their skin, and that toxin can actually cause paralysis of an animal if they try to eat the frog. So this frog can be really brightly colored and nothing messes with it. So like animals walk by, nope. They just know because of that color that that's like a danger color. So they don't have to camouflage themselves. They have this, and this is one of them, this histrionicotoxin, and it actually will cause paralysis of an animal if they actually put it in their mouth even, because it's in the mucus that's on the surface of the frog. So toads are dry skinned, but frogs are like wet or damp, kind of shiny. So one thing that's interesting is that the people that live down in the rainforest in South America, they realized this. They would take their arrows and hold the frog with a stick, not touch it, Pretty smart. Hold the frog with the stick and actually rub the ends of their arrows on the back of the frog. So it would get some of this toxin. So then when they shot a deer, what would it do to the deer? So the deer would drop. So that way, even if you didn't get like the perfect shot, that toxin would actually like paralyze the deer so that it didn't end up running away. So it made them much more successful at hunting, having this realization. But it's because that chemical is super reactive and actually has this like neurotoxin effect. Okay, but now everybody grab this little sheet. Does everybody get one of these little sheets? Okay, and it's laminated. Okay, so notice in the upper left corner, do you see that alkane, C to C to C to C, all single bonds? Alkenes with the double bond between two carbons. Alkynes have a triple bond between two carbons. You will have this when you take an exam. So you don't really have to like put this on your note card. You just have to remember how to use these, like being able to identify the functional groups. We are not going to name them like we were naming hexanes and cyclopentanes and such. We aren't going to name them. This is purely just looking at organic molecules and picking out these functional groups. So here's the third one. The third one, it should be in your upper right-hand corner. That is what they call an aromatic. So an aromatic is a carbon combination. It's 6 carbons, and those 6 carbons have alternating single and double bonds. So if I have this one carbon, so you've got the carbon here, there's a double bond to this carbon, but then the next one's a single bond, then I have a double bond, then I have a single bond, a double bond, and then a single. So remember I said triple bonds are really reactive. Double bonds are more reactive than single. These are actually pretty stable because that double bond can actually switch with single bonds adjacent. So you will sometimes see it might be drawn with the double bond starting in the upper right corner. It might be drawn with the double bond starting in the upper left corner, like those two down at the bottom. So those bonds kind of switch back and forth, which actually makes them really quite stable. So aromatics are typically pretty stable. You might see them drawn like this though. So don't let that throw you. What that is showing is it's the 6-membered ring, but it's trying to show that it's almost like 1.5 bonds each. So you'll see that circle kind of shape to it. All of these are referring to the exact same thing. And that last picture shows you 5 of those rings all linked together, which is really common in some plastics. They were named aromatics though, because initially these chemicals, when they found them, they're pretty smelly. And so they were like, they gave off an aroma. So they had a smell to them. That's how that name came about. These are still just hydrocarbons though. They're just carbons and hydrogen, but they're just different bond type of combinations that you can find. The rest of these are all, so there's the alkenes, alkynes, the aromatics. These are the ones that are just the hydrogen and carbons. But now if we throw oxygen into the mix, oxygen can be found in a lot of different places in organic molecules. It can be found between 2 carbons. It could be found at the end of a chain. It could be hanging off the middle of a chain. It could be a single bond. It could be a double bond. So it's combination. And if you kind of like make sure that you look at your little card, your functional group card, because you'll have that one. We'll just go through them. And then what I want to do is I want to see if you can pick out some of these when you see a big molecule with a lot of them. Okay. So the first one's called an alcohol. So an alcohol is when you have an OH hanging off of a carbon, but there's nothing else on the carbon. So notice that that carbon just has a hydrogen. That alcohol could be in the middle or it could be on the end. Sometimes it's hanging off of the middle of the chain. So it could be like this, CH3OH. That's an alcohol as well. That's actually isopropyl alcohol or rubbing alcohol. The one at the top is ethyl alcohol or ethanol, which is what you typically think of as like alcohol, right? Like in beer and wine and spirits, things like that. That's that top one. So if you have just an OH attached to a carbon with nothing else on the carbon, it's an alcohol. An aldehyde is always on an end of the molecule, and it's when you have a double bond oxygen on a carbon that has a hydrogen. So see how that's different than the alcohol. It's written differently because see how that one looks like CHO and the other one looks like COH. It's written differently, but when I show it, when I give it to you, I will always give it to you like with the bonds indicated so that you can see that this is the OH for an alcohol and you see that it's a double bond to oxygen to a hydrogen for an aldehyde. The key things to remember is the double bond oxygen is always on the end and that carbon's going to have a hydrogen. So looking at the third one, do you see how the third one looks like a combination of the two? The third one, called a carboxylic acid, it looks kind of like an aldehyde and an alcohol got together, right? Because they both it has both of those. There's a double bond oxygen and an OH on that end carbon. So this will always be at the end of a chain, never in the middle. Alcohols can be in the middle or on the end. But aldehydes are always on the end of a chain. Carboxylic acids are always on the end of a chain. And you can recognize carboxylic acids because there's two oxygens. One is a double bond, one is an OH. These two are the next two are the only nitrogen containing functional groups. So if there's a nitrogen, it's either an amine or an amide. Okay, so if you see a nitrogen, you know it's an amine or an amide. It can't be anything else. It's an amine if the nitrogen is attached to a carbon without an oxygen. So when I find a nitrogen, I look at the carbon that it's connected to, and I look to see if there's an oxygen on it. If there isn't, it's an amine. If there is, it's an amide. So notice how this one, I find this nitrogen, and I look at this carbon, and I see that there's an oxygen attached to it. That's how I know it's an amide. So that's kind of the common way that you'll see an amide. The oxygen's double bonded to that carbon. It might be sticking up, might be sticking down. But if you see a nitrogen, look at the carbons that are attached to the nitrogen and look for oxygens. If there is, it's an amide. If there isn't, it's an amine. But you know it's going to be one of those. So you can kind of see the amines and amides. Okay, so here's the last ones. So there's still 5 more. A couple of them I think are pretty simple, but these 3, ketones, ethers, and esters. So a ketone is kind of like an aldehyde, but instead of being at the end of the chain, this is always in the middle. Ketones are in the middle of a chain. So notice like the way I drew it, it was like CCC, and there's a double bond oxygen off the middle one. Whereas an aldehyde, you see the double bond oxygens off of the end carbon in the chain. So ketones are always in the middle of a chain. You'll never find them on an end. It's just a double bond oxygen sticking off of a carbon. Acetone, like nail polish remover, that is a ketone. Ethers are when the oxygen is part of the chain. So if you have carbon, carbon, oxygen, carbon, so it's just a single bonded to carbons on either side, that's where the oxygen's part of the chain. And an ester is kind of like a combination of these two. Kind of like with the alcohol and the aldehyde, look at the carboxylic acid. If you took a ketone and an ether and put them together, they look a lot like an ester. Ester has 2 oxygens. One's a double bond oxygen, but there's an oxygen connected to that carbon. So if you look at this carbon, you can see there's 2 oxygens attached to it. That makes it an ester. If you look at this carbon and there's only 1 oxygen double bonded, then it's a ketone. A lot of your fruit flavorings are esters. Ethers were used as some of the early anesthetics. Like, have you ever watched like those crime shows where somebody like puts something on a cloth and like grabs the girl and puts it up to her face? So that's usually an ether. Some type of ether, and so they're like, whew, like they swoon, faint. That's an ether. Last two, thiols. Thiols, easy because anytime you see a sulfur, it doesn't matter what's around it. It doesn't matter about anything else. It is a sulfur and it's a thiol. I always think of them as stinky. They're like, if you cook eggs, like if you boil eggs, you know that smell, that's a sulfury kind of smell. If you ever go by the swamps, like especially in August when it's kind of like hot and muggy and you get that same sulfury smell, it's because of decaying, rotting wood that gets that smell. But that's the thiol in the organic molecules. And then the last one called a phenol. It is an aromatic. You see the alternating single and double bonds. So whenever you see that, alternating single and double bonds, look to see if there's an alcohol. See if there's an OH attached. If there is, it's a phenol. If there isn't, then it's just an aromatic. Aromatics don't have an alcohol group attached. So it's kind of the combination of an aromatic and an alcohol. Phenols were actually some of the very first surgical disinfectants. They began to realize that hand washing, cleaning surgical instruments, cleaning surfaces decreased infection rates dramatically. So it was terrible. Back in like the 1500s, about 30% of women died from what they called childbirth or childbed fever. And so what it was is you had a doctor that delivered this woman's baby. His hands are covered in blood. He goes to the next woman and wouldn't even like rinse his hands. Okay? He'd go from woman to woman to woman. So if this woman had an infection, he then took and introduced it into the next woman when he was delivering that one, and that one, and that one, and that one. So it was very common that people died after childbirth because of an infection. Because you know when that placenta pulls away, that's really like a big open wound. And so by not having any kind of disinfection, any kind of aseptic technique, they were just transmitting it. It was really bad, especially with people that were poor, people where they had just not enough doctors for patients. Well, they realized this guy started doing research, and he found like if he even just dipped his hands in phenol in between, that infection rates dropped dramatically. So this became kind of the common disinfectant that was used. It is irritating to the skin, so it is kind of strong, like it's a component you find in the Lysol cleaner. They even for a while would have somebody that would spray this into the air during surgery. So you would have this misting of phenol because they believed that it helped to keep down infections. It's just a disinfectant. It's meant to clean floors and non-living surfaces, so it's a bit rough. It's a little bit rough to be like spraying onto open wounds and such. It would cause a lot of irritations. Antiseptics are things that you can put in contact with living tissue. Disinfectants are meant to clean dead stuff or like inanimate objects, nothing that's living. But it was like kind of the start of this realization about microbes and infections. So just remember, like phenol, look for the 6-membered ring and look for the alcohol or the OH. And that could be sticking off of anywhere. So the OH could be sticking off the right, the left, the bottom, any carbon in the ring. It doesn't have to be perfectly like sticking just up the top right. All right. So let's look at a couple of them. So the first one is aspirin. So this is acetyl salicylic acid. We're actually going to make this in lab. So looking at this one, look at all of your functional groups are on here. There is actually 3 functional groups in this one molecule. So when I look at them, I always look for 1, I look to see if there's a sulfur because that's a thiol. 2, I look to see if there's any kind of 6-membered rings, alternating single and double bonds, because I know that that's aromatic or a phenol. Then the 3rd, I look for nitrogens because nitrogens are amines or amides. And then the last I do is the oxygen because the oxygen's got the most possible ones. You've really got to kind of look at how they're arranged. So what do you see? When you look at aspirin and look at your chart, what is something that you see? It's not a phenol because it doesn't have an OH, but it is an aromatic. Does everybody see this one? So notice that that's a 6-membered ring, but there's no OH directly connected to it. So this would be an aromatic. The one at the top, it's sticking off of an end, It's a carbon with 2 oxygens. One's a double bond oxygen, one's an OH. What is that? This is a carboxylic acid. So just split it into like 3 syllables, carboxylic acid. Yep. And then the third one, here's this other one. So notice, like, you might have seen just one oxygen. When you see one oxygen, always look to see if there's an oxygen like by the side, like if they're kind of grouped together. So this is in the middle of a chain. It's a 2 oxygen group in the middle of a chain. It's an ester. So look at your chart. Do you see what the ester looks like? Can you see that? How that matches this? So in that one above, the single oxygen goes off to the left, and the one in your chart, it goes off to the right, but that's the same, so that would still fit. Okay, what about Tylenol? So Tylenol is acetaminophen. Okay, there's this aromatic, but look what it's got attached. Yep, so this is a phenol. Some people call it a phenol. So you see the phenol, see how it's different than the aromatic. So look for that 6-membered alternating single and double bonded ring. Just look and see, is there an OH anywhere? Okay, so that's all that. So now, what do you see next? See the nitrogen? As soon as you see a nitrogen, look at the carbons next to them and look to see if there's a double bond oxygen on any of them. Does this one have one? Yes. If it does, that's an amide. If it doesn't, then that's an amine. That's an amide. I was already thinking ahead. Okay, what about the Advil? Advil is ibuprofen, so that's the next one. These are all pain relievers. Well, except for the saccharin. What's up at the very top? It's not an aldehyde, so it's close to an aldehyde, but notice that the aldehyde, that double bond oxygen has a hydrogen. It's that carboxylic acid thing again. So this is the carboxylic acid. What else? There's only one other thing. So these are just carbons, 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 but this, that's an aromatic. So it's just a 6-membered ring alternating single and double bonds, no OH attached, so that makes it an aromatic. So let's do this one, and we'll quit. So this isn't a real molecule, I just made this one up, okay? And I just did this, so there's actually 9 functional groups, okay? So take a minute and look, see if you can find a couple of them. So remember the things that I told you to look for first. So there's the ones that are like pretty easy, and then work your way up. See if you can find 9. I'll give you a minute. Find as many as you can. All right. So did you find any? Just call one out.
Phenol.
Where did you find the phenol? In the very middle. Good. Did everybody find this one? So there's the 6-membered ring, alternating single and double bonds with an OH sticking up. So this is a phenol. And you see a thiol. Yeah, that's the one that I say look for first. Because if you see a sulfur, it's a thiol. You got one, okay? No matter what else is there, it's a thiol. So that's the one that I check off first. Then I look for my rings. There's this aromatic. So see the other 6-membered ring. Notice there's nothing but carbons and hydrogen. So this is the difference between the phenol and the aromatic. The aromatic will not have the OH, the phenol does. Uh-huh. An amide where? Okay. Yep, so you found the nitrogen, right? Once you find the nitrogen, look at the carbons on either side. If there's a double bond oxygen, it's an amide. Okay? So what else? The next one, the other one. Do you see the other nitrogen? Do you see? So when I look at this carbon, do you see that the carbon it's attached to doesn't have an oxygen? So that means that this is an amine. So look on your card. So notice that if the nitrogen doesn't have an oxygen, that's just an amine. If the nitrogen is attached to a carbon with no oxygen, it's an amine. But if the nitrogen is attached to a carbon with the double bond oxygen, that's an amide. It's going to be one of the other. I don't see any other nitrogens. So those are all the nitrogens. We named the thiols, we named the aromatic and the phenols. So all the rest of these are oxygen groups. So, you see an aldehyde. Where's the aldehyde? Upper left, lower, like left. So here. So that's not on an end, that's like in a middle. Do you see this? So that carbon, that double bond oxygen is attached to, has an oxygen attached to it as well. So that would be a what? Carboxylic acids are always on an end, aldehydes are always on an end. Those are kind of like things to try and remember or put down in terms of ways to find these, because these oxygen ones are probably the more complicated. The nitrogen ones, it's one or the other, or aromatic or phenol, thiols a given, but this one, it's an ester. So ester is always in the middle of a chain. It's a carbon with a double bond and an oxygen in the chain. What else? A carboxylic acid, and it's where? Okay, at the very top or the middle? The middle, right. So you see this? So carboxylic acid's always on the end. It's a carbon, double bond oxygen, and an alcohol on it. That's the carboxylic acid. Yes, and the one above is also always on the end. It's the aldehyde. Do you see that one? There's only one more, because we did 1, 2, 3, 4, 5, 6, 7, 8. Yeah, there's one more. Yes. See it right there? See, it's just a carbon in the chain with a double bond oxygen sticking off. So this is a ketone. Okay? So we're going to do more of these because look, I got more. And I got some more. Okay? So this is not the only one, but we'll go through and do some practicing of them. There is a functional group dynamic study module. Okay, so if you feel like, okay, I think I'm starting to understand those, this would be a good time to just go ahead and do that one, just because it'll have you go through, and it'll show you a molecule with only one functional group, so that one's not so bad. Please don't take these home with you. You can use these on the exam, so just like the periodic table, I will give you this, but this functional group handout is posted in Moodle. So if you want to use it to do your dynamic study modules or to do any kind of practicing, that would help because then you got it right there. But the ones that I have that I laminate, I just reuse them, kind of like I do with the periodic table. So leave those, but they are posted. It says it's called the functional group handout. It's in exam 2 module in Moodle.